Hello students, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In the series, we've been working through the brand new June 2026 Chemistry Regents cluster by cluster. This is the 8th video in the series where we're going to take a look at the CHIPS PFAS versus PLA cluster. If you're looking for a different cluster, you can take a look at the playlist linked in the description below. As always, we're going to start by reading the cluster for understanding. So it says that companies that produce snack chips consider several criteria when choosing packaging materials, including cost, environmental impact, function, and appearance. Prior to 2010, most chip bags were made with PFAS, which were made from petroleum, a non-renewable source. PFAS molecules are very stable due to the presence of multiple carbon-fluorine bonds. Because of this, PFAS are sometimes called forever chemicals because they do not break down in the environment. In 2010, a new chip bag made from PLA was introduced. PLA is a bioplastic made from lactic acid, which is produced from renewable resources such as sugar or corn. During the production of PLA, many lactic acid monomers join together to form long chains by removing a small molecule. Figure 1 represents one step of this process. So question 33 asks you to identify the missing product in the simplified process to produce PLA to demonstrate the conservation of atoms. There are two ways that you can do this. The first way, which is arguably the more challenging way, but probably the way I would think most students did, was by counting up all of the atoms. So you could make an inventory on both sides of carbon, hydrogen, and oxygen. And you can count up all of the atoms on both sides. All right, so here we go. 1, 2, 3, 4, 5, 6. Okay, so 6 carbons. I'm going to just pause and do it myself. So after I counted, these are the numbers that I got. And what you could do is realize that on the product side, what we ended up doing was removing 2 hydrogens and then removing 1 oxygen. Well, what is the name of a formula, or what is the name of a compound that has 2 hydrogens and 1 oxygen? Well, that would be H2O, water. The more easy way that I see, at least, I don't know if you see it like this, is maybe you can see that we're adding 2 monomers together to form 1 polymer. If you look at what's actually being removed, you can see we are losing H2O. Anyways, let me know in the comments which way did you do it. Right, question 34 says, explain how the attraction for electrons between the elements that supports the function of PFAS as a forever chemical is more stable than the carbon-hydrogen bond in a PLA molecule. Hopefully, you had this experience when you took the Bend and Stretch State Lab because they talked about different bond energies and attractions and all that fun stuff. Anyways, if a carbon-fluorine bond is more stable than a carbon-hydrogen bond, this means that there's a stronger attraction for electrons. Like you'll have a very short bond length, and the molecule will be held together very strongly. Thus, it's a forever chemical because it doesn't really get broken down. In the comparison of these two bonds, where we have carbon-fluorine and carbon-hydrogen, it's important to note that fluorine is the most electronegative element on the entire periodic table. It's all the way on the top right. So this is going to be much more electronegative than this. So what they're looking for is fluorine's very strong attraction to electrons makes the bond a lot more stable. All right, moving along. says that polymers such as PLA can be modified to improve their properties. In 2025, scientists found that the rate of decomposition of PLA can be increased by replacing some of the oxygen atoms in lactic acid with a different element to provide sites of weaker bonding. Polymers can also be modified to affect physical properties. Cross-linking establishes electrical forces between different polymer strands, which improves the durability while compromising flexibility. Figure 2 shows the configuration of linear and cross-linked polymers. The illustrated circles represent individual monomer units. When I read this, I'm thinking back to that state lab where we had to make our own polymer, gelatin, and where we were looking at the PTFE tape. So this is actually a perfect example of the two polymers that we worked with throughout the year, right? This linear polymer, this is the plumber's tape, the PTFE tape. And then this cross-linked polymer, this is going to be my gelatin. And you remember in this bend and stretch lab, you could not stretch the polymer this way. That didn't work, but you could stretch it this way. So it was still a little bit flexible. You couldn't stretch the gelatin either way. It was just rigid, it did not move. So that's kind of describing more durability. So that will be helpful with one of the questions. But anyways, 35, which row compares the properties of the listed element to oxygen replaced in lactic acid to increase the rate of decomposition? I'm thinking if we want to replace an oxygen atom with something else, we want it to have the same number of outermost electrons. So let's use our periodic table to figure out which one that is, either nitrogen or sulfur. Over on my periodic table, here's oxygen, and would you look at that? Sulfur is right below oxygen. So I'm thinking this has got to be sulfur if we're just switching out an element. So I'm going to just get rid of row 1 and 2. And by process of elimination, we kind of have choice 3, right? Because same number of valence electrons, it's the only one that states that for sulfur. That was my thought process, but we could go through and actually eliminate all the others by looking at the atomic radius. We know that sulfur is a bigger element than oxygen, right? So it's going to have a larger atomic radius, so that's not true. And then as far as its ionization energy, well, the trend for ionization energy follows that of electronegativity. Right, so the ionization energy of oxygen is going to be greater than that of sulfur. Sorry, and I'm getting cut off here. So that would also make that false. Okay, as for nitrogen, nitrogen has different valence nitrogen has different valence electrons, so we can eliminate choice 1 because of that merit. The atomic radius is going to be larger for nitrogen. That's because our trend for atomic radius goes from top right to bottom left. So that is true. And as far as ionization energy for nitrogen, if we look back over here, ionization energy is going to be a little bit lower for nitrogen than it is for oxygen. All right, so by that, we could actually cross this off for choice 2. Okay, for number 36, which row describes how the electrical forces in a cross-linked polymer affect the durability and flexibility of PLA? Well, in the cross-linked polymer, you can see that we have many more attractions. So we have these attractive forces. They're not going to be repulsive, so we're going to get rid of 3 and 4. In terms of the durability, the question does mention durability somewhere. I know we read it. Where is it? right here. It says that cross-linking establishes electrical attractions, which improve the durability. So that means durability would increase, but the flexibility decreases, and it also says that because it compromises flexibility. This has got to be choice one. All right, and then the last part to this cluster, drinking water may contain PFAS. There are two types of PFAS, PFOA and PFOS. In 2024, the EPA set a limit on the maximum contaminant level in drinking water for each of these chemicals as 4.0 nanograms per liter. Figure 3 shows a portion of the annual drinking water quality report for 2021. It then wants you to make a claim as to whether the drinking water samples in Figure 3 are safe with respect to PFOA and PFOS. If the safe limit is going to be 4.0 nanograms per liter for both of them, and they're both at these levels, which are clearly below 4.0, our claim must be that the drinking water is safe. But watch out because it wants you to cite numerical evidence. So that means you have to actually list the numbers that were detected. So this is what I got. All right, and that's it for this cluster. If you found the video helpful, be sure to like the video and subscribe for more walkthroughs. When you're ready, you can find the next video in the description below. Happy studying.